All right, welcome back for another episode of Connie 352. Today we are going to be discussing heat pumps. Heat pumps are just kind of a special type of refrigeration cycle. Now, they've got all the same normal parts of refrigeration cycle that all the others have, right? And here's the basic refrigeration cycle diagram. For this class, why don't you go ahead and get out the lecture notes, the packet section, and also there is a PowerPoint on ground source heat pumps. So get both of those out. This diagram is the same diagram we've already looked at. It's on page 21 of the lecture notes. And it just shows our typical components: compressor, condenser, thermal expansion valve, and evaporator. A ground source heat pump, though, changes two things. One, instead of running ambient air through the condenser, it runs water that we pump through the ground in tubes. Basically, we change our heat rejection to the outside. We pass water through this condenser, and then we bury these tubes down in the ground, and I've got pictures of them that I'll show you here in a little bit. But we're going to take this water that the condenser heats up, and now it buries it in the ground, and we reject that heat to the ambient ground instead of the ambient air. One important thing to note: see these temperatures? And like I said, I'm on page 21. But these temperatures are for ambient air. For the ground is much cooler. Even in summer, obviously, it's much cooler than the ambient air. So the water that we pump down into the ground can also be much cooler. If that average ground temperature is, say, 60 degrees in the summer, the condenser water temperature only has to be about 70 degrees to reject heat to that ground. We got to have heat transfer. We have to have a difference in temperature. If the ground ambient temperature is 60 degrees, if the water that we put through a heat exchange, through some pipes that make a heat exchanger with the ground, that can be just 10 degrees warmer. And because of that, the outlet at this condenser can be much cooler. Therefore, the compressor has to compress this high temperature, high pressure gas. It doesn't have to get that gas as hot to reject heat, so the compressor doesn't have to do as much work. It doesn't have to increase the pressure here as much. So if we're rejecting heat to the ground and that ground is cooler than the ambient air, we can actually save energy. All right, so there's one different part, is that it rejects heat to the outside, but also what the heat pump does is that I don't have all the different pipes shown on here, but I just want you to think about it being able to take this hot pressure gas, and instead of sending it to the water side, it could send it over here to the evaporator side. In other words, the heat pump has the ability to change the direction of energy flow. All right. So it goes from the compressor over to the air side. Remember, the condenser and the evaporator are nothing more than two different heat exchangers. The heat pump has the ability to change where it sends that high temperature, high pressure gas. It could send it to the ground loop rejection, or it could send it to the air side, which is return air. So it can either pull air out of the ground and send it to the house, or pull air out of the house and send it to the ground. By doing so, it allows the refrigeration cycle to accomplish both heating and cooling with one piece of equipment. All right, let's look at some pictures to kind of get us a better idea of what's going on here. All right, so go ahead and open up the ground source heat pump presentation, and let's just take a look at these. First picture, here is a picture of a residential system. It's really just a box in the basement somewhere. See these red hoses? Those are connected to a pump on the wall that pumps water through the ground and then back to the heat pump. And like I said, that's what this box is. The silver part on the top, that's just ductwork. All right, let's have a look at a few more. There's three main options for using the heat pump and heat rejection. We can either reject it to the ground in a long straight loop like this. We could reject it to deep wells, or we could do it to like a pond. All right. Here's a different diagram, but it shows the same thing. The compressor, in this diagram, the compressor's at top, the expansion valve's at bottom. High pressure, high temperature vapor goes through the condenser. Low pressure, low temperature liquid goes through the evaporator, and it goes round and round. The heat pump, I want you to think of it as the heat pump can just switch directions on where it's sending that high temperature vapor. All right. And that's it. It's called, sometimes you'll hear this term, it has the ability to reverse the direction of the hot refrigerant. The compressor doesn't actually spin backwards. It just, through piping and valves, it can automatically reverse the direction of the refrigerant. All right, let's keep going. So, once again, here's another schematic. I've got a fan in that heat pump. I have ductwork, just like with a normal furnace. All right, return ductwork, a coil, and supply air duct. No furnace in such that there's no gas being set on fire, that type of thing, but it's just a refrigeration cycle. All right, let's take a look at this. A pump, probably a small one on the wall, pumps water out to the ground, and we bury a bunch of tubes in the ground and pumps it back. Next picture is the guts of one of these. Down here is the heat exchanger with the water. Up here is the heat exchanger with the air. Inside here are the pipes, and if you look right here on this picture, that it looks like kind of a brass cylinder. That's called a reversing valve. That's the valve that's able to change which heat exchanger it sends the hot refrigerant vapor to. Next, so three types of the earth connections. And one of these, the groundwater, I'm not going to talk about much because it's not really allowed in the state of Iowa or in most states. All right. Deep wells. They're going to go out and drill deep vertical wells in the ground, probably around 200 feet, maybe even deeper. We're going to put tubes down through those wells. The advantage here is that it doesn't take up, in terms of surface area, it doesn't take up a whole lot of space like these others where we just direct bury it just a few feet down, where those take up quite a bit of surface space. This system, where it actually pulls groundwater out, the reason I'm not going to talk about that one much is that the groundwater, if you take groundwater, put it through this heat exchanger and heat it up a few degrees and then dump it like at grade level, that is considered a pollutant. And you have to get special permits to do that. And the state of Iowa is reluctant to do it. They don't do it much anymore. They used to do it quite a bit. So I don't want you to think about that one where they're actually pulling up groundwater. The important thing to understand is in these other systems, the water in the pipes never touches the ground. It's always in the pipes. The pipes set up a heat exchanger between the water in the pipe and the soil that's outside of the pipe. But important thing, the water is just continually circulated through those pipes. It never actually touches the ground or the earth. Let's have a look at this next picture. All right, I got a couple of diagrams, but also a real life picture. these are for vertical loop systems, like for a large building. Probably odds are that some of you that are taking this class went to either an elementary school or a high school that is heated and cooled through ground source heat pumps. And on a large building like that, like a high school, for example, Southeast Polk High School is done with ground source heat pumps. They have a bunch of these deep wells buried in the ground, hundreds of them actually. Each of them dug about 200 to 300 feet down. So the advantage here, and there's several of this. The advantage of using the deep wells is that it doesn't take up a whole lot of space, and you get a much better average ground temperature. Once you get down past probably 15, 20 feet past the surface, the ground temperature doesn't change much during the course of the year. It's probably around 50, 55 degrees. Doesn't really even know that winter is going on up above. So you get this nice even temperature to put your heat exchanger in. The downside of the wells is that each of those wells, you have to get a well drilling rig and a certified well driller to do the digging. That ends up being very expensive, to the tune of around each well is probably $3,000 to $4,000. You can spend a lot just on digging the holes. Now, other loops that are just buried in the ground, those are much cheaper to put in, but they take up, and if you see this is called a slinky system, where they just dig a trench, put a bunch of the pipe in there, and they've ran them in loops, and then they just cover it up. That shallow, the picture here is probably not for Iowa. Probably further to our south. For Iowa, I'd probably want this to be at least 6 feet or so down below the surface. That kind of is a minimum. A little bit deeper would be even nicer. But the important part here is that they are digging a hole, or we could use a ditch witch like a trencher, and putting it in that way. Now, here's a diagram of that, the horizontal loops, where we go out and dig around, and then just bury these about, like I said, about 6 feet down. Here's a open loop, a pump and dump type of a system, which I said is heavily regulated and I'm not going to discuss. Here's what's called a pond loop. Same idea. I mean, they all have the same idea. We're rejecting heat to the outside and we're pulling heat in from the outside. But a pond loop, if we have a pond, we just dump a bunch of this tubing in the pond itself and then circulate it out and back. There's kind of a diagram of this in the bottom right corner. The pond loops are nice in that there's no excavation here. Now, that's assuming you already have the pond. It's probably not cost effective if you're digging a pond just to put the heat pump system in. But if you're putting a building and there's already a pond there anyway, this gets to be pretty cost effective, because now all you have to do is put the tubing in the pond and then hold it down. Notice the very, very scientific cinder blocks, or concrete masonry units, would be a more accurate term, that are holding these down as this pond fills up. They're just in the process of burying this, and it's just settling to the bottom. There's some really large examples of this. Probably the biggest example is the Great River Medical Center in Burlington. It's a 700,000 square foot medical care. It's a whole campus. At the time, it was the largest water source geothermal system in the country. I don't know if that's still the case. It was about 1,500 tons worth of cooling capacity. And the lake, and this picture here on the right is the lake as it was filling up. They just put in the tubing. You can kind of see the light black tubing lines out there. They just put it in, and it was still, the pond was in the process of filling up. You get about 100 tons of cooling capacity per acre of lake. So projects like this needed a very massive lake. They were going to do the lake anyway for stormwater retention, so it made sense to do it this way. Now, like I said, I don't think I'd recommend digging a lake just for a heat pump system, though. All right, here, this graph kind of shows temperature versus depth. If you look at, okay, here this is about a foot down, 6 feet down, 15 feet down. Once you get down to like 15 feet down, the average temperature, if you look at the temperature on the right, it's like right at 50 degrees Fahrenheit. It stays very constant through the course of the year. Once you get deeper and deeper. All right, let's keep going. Next couple pages are just showing the process of like the drilling rig. Okay, most cost effective, and a heat pump is not always cost effective, to be perfectly honest. Sometimes it can be drastically expensive. It depends. Here, most cost effective when you have heating and cooling, and I'm going to say you have a pretty balanced load between heating and cooling. All right, you have like an even range of cooling and even amount of time that you spend during the course of the year heating. Here, for heating, it really only makes sense when you have low electricity costs and high gas or high oil costs. Electric rates are the key here. You've really got to analyze electric rates. Years ago, when I was doing energy studies for schools, think like in the year 2000 to 2005, it was a much different time because electricity was far cheaper and natural gas was getting more and more and more expensive. And later in this class, we're going to do a cost analysis of some energy systems. But in general, I want you to know that year 2000, 2005, a lot of heat pumps were put in because electricity was cheap and natural gas was expensive. One therm of natural gas is 100,000 BTUs. Okay, right? I mean, that'd be a good value to write down for later in this class, but I'll state it again later. But 100,000 BTUs is the potential energy in what we call a therm of natural gas. It's about a cubic foot of natural gas. So that in the year 2000, a therm of natural gas was selling for around $1.50, $1.50 per therm. And we were thinking it was just going to keep going up and up and up. If you look today, I just did an energy study last week for a school, and their natural gas costs for the last couple of years have averaged 50 cents a therm. What has happened in the last 20 years or so is that we have found a lot more natural gas. Fracking and deeper drilling have found a whole lot more natural gas. Natural gas is getting cheaper and cheaper. However, electricity is going up in cost. And we can go on and on as to why this is, but in essence, it is getting harder and harder through regulations to produce electricity cheaper by burning coal. Far and away, if we look at the choices that we have to generate electricity, we could talk about burning coal, we could talk about burning natural gas, we could talk about nuclear power, or we could talk about wind and solar. Far and away, the cheapest input kilowatt comes from coal. Coal is dirt cheap. However, coal is dirty. Coal produces a lot of pollution. Environmental regulations are getting more and more difficult to produce electricity with coal. Natural gas burns cleanly, I'm not going to say it's zero emissions, but it does burn a little cleaner than coal, and it is also cheap right now. However, both of those, politically and in environmental regulation-wise, it is very difficult for a power plant to put new coal and natural gas plants online. For sure, coal is almost impossible. However, zero emissions at the site, I should say, fuels like solar and wind power have gotten a lot more use. I'm going to talk a little bit more about the different options that we have for generating electricity later in the class, but the thing about solar and wind energy is that they do not cause your power costs to go down compared to coal or compared to natural gas or even compared to nuclear power. Dollars per kilowatt hour, wind energy and solar is more expensive. So our electric rates have been going up while natural gas has been going down. In the 2000s, a bunch of schools were doing geothermal heat pumps. And now you don't see near as many new construction geothermal heat pumps going in because of the difference in electric rates. All right. Let's keep looking. Let's look at some more. This next page here, this picture on the right, this is actually a drilling rig. Something important to know about drilling rigs, putting in the resident a geothermal system that uses the buried pipes. This will turn whatever field or yard or wherever it is that you're putting this in. It's going to look like a mud pit after they're done. All right, the drilling rigs make a terrible mess. The heavy equipment makes a terrible mess. One year, I was talking to a school district about putting a geothermal heat pump in their new building that was kind of on a campus that already had some existing buildings, and they had a baseball field, and then they were going to build right next to it, and they're like, hey, we got some green space. How about we use the baseball field as our field area for the geothermal heat pump system? I'm like, okay, that's awesome. I just want you to know that when they get done drilling all these holes, it's not going to look like a baseball field. I mean, you're going to have to, are you okay with destroying the field and then rebuilding it new after they're done? And they're like, well, wait, no. We don't want to destroy the baseball field. We just want to put the pipes underneath it. And, the question was, well, how do you think they're going to get there? So we had this discussion. They decided it'd be too expensive to tear up the baseball field, so they decided not to go with the geothermal heat pump system. Just know that the work to put it in is extensive, and it'll tear up whatever field that is there. All right. This slide, and I took this slide from basically a seminar years ago on geothermal heat pump systems. Talks about short payback periods. This isn't necessarily true anymore. Payback period. It's a payback period is, well, how long is it going to take if I spend extra money today on a better system? How long would it take to pay that back? When natural gas was expensive and electricity was cheap, geothermal systems had some pretty short payback periods, but this is not true anymore. All right, let's look at some of the other advantages and disadvantages here. Land availability, kind of like I was talking about with the baseball field and destroying the baseball field. Land availability, you've got to have land to actually do this. Now, the nice part about a geothermal system is that inside the building and outside the building, visibly above grade, you don't see a lot of equipment. It's actually kind of small. In a commercial building, those geothermal heat pumps are going to be like up in the plenum space and attached to a little bit of ductwork. So you lose less space in the building and you use less visible space outside the building. Remember the cooling towers from the chiller system. You don't see anything from the geothermal system. All those tubes are buried under the ground, so you don't see them. Now, something important to keep in mind is that you can't build on top of them. You can't put like a parking lot on top of it, and you can't put a building on top of it. So wherever you put those tubes, even though they're buried and out of sight, you can't really put much on top of it. Because those tubes are not visible, we have a reduced vandalism risk, which is true, and that's something that buildings do worry about. All right, let's keep going. Now, sometimes, right, here's an example of a horizontal system where they're just using a trencher to dig a hole, and then they're going to put, you can just see right there, if you look at this on your own screen, right, you can see the tubes, they're running them along the ground there, and they're going to put them down in the trench as it's dug. And then here's another picture of a job site with a drilling rig. Dirty, muddy, messy. This is just, it's a slow process and expensive process. So let's switch over to the lecture notes here. All right. And we got to go ahead, or back, I should say. There we go. Let's talk about advantages and disadvantages of a ground source heat pump compared to some of the other systems. All right, advantages. Utilize the ground as a heat exchanger. So it's out of the way and out of sight. Architects love that. Let's compare it to like a large chiller. Like, let's say that we were going to do either a chiller boiler system or a ground source heat pump system in a school. The way this works is we're going to have one ground source heat pump for each and every room. We'll have like one or two maybe big chillers in a mechanical room, or a ground source heat pump in every room in the school. Those are our choices. The ground source heat pump isn't going to be visible, and the maintenance on each of these heat pumps is easier. A large chiller that costs maybe $100,000, $200,000 or more dollars, that is a complicated machine that requires very, very special skill. A heat pump per room in a school, there's not any real difference between a commercial heat pump and a residential heat pump when we're talking about the ones for individual rooms. So the skill for the heat pumps is lower, but we have one in each room. On a large school, that could be hundreds of compressors that need maintenance. So while the maintenance is easier skill-wise, there's a lot more of them to go service. Also, they are located in the ceiling area. Usually, you might see on some schools, they might be in a closet or maybe even a console that's like on an exterior wall. But most of them are going to be hidden in the ceiling. The maintenance there has to be done in the occupied space. A chiller maintenance is done in a mechanical room. For a heat pump in a school, it's done in the ceiling in occupied space. So while the maintenance is simpler in skill, it can be more complicated because of having to access it through the ceiling and have to do it on a ladder. All right, ground source heat pumps are usually more efficient than the other refrigeration cycles other than a water-cooled chiller. They are normally more efficient, kW per ton of cooling. They're more efficient than normal split system air conditioners, rooftop units, even air-cooled chillers. They're more efficient than all of those. The controls are pretty easy. Once again, very similar to residential. I've got a thermostat. I put it on the wall. It either puts it in heating, puts it in cooling. It's very simple. And if one heat pump fails, it's not like we lose cooling for the entire building. All right. Those are all good advantages. Disadvantages. Adding on later, like let's say that you build an addition, you can't just make that buried tubing bigger. It's kind of difficult to add on to later. It has a very high first cost because of the excavation necessary. The excavation necessary to put the wells in. Those wells are probably going to be spaced out about every 15 feet at grade. So as you're 15 feet apart, another well 15 feet, another well 15 feet. That ends up being a big, for a big building with a lot of cooling load, that ends up being a really large space because you need about one well for every ton of cooling capacity. I mean, that's a good, decent rule of thumb. So if you're having one well per ton, if you've got 1,000 tons worth of cooling capacity like a large chiller would have, you need 1,000 of those wells in the ground somewhere, and that ends up being a big area. If something was to happen to the underground tubing, like it was to burst or somebody was to cut it accidentally, excavating for something else, that can be a major problem. All right. Now, already talked about maintenance in occupied spaces. Algae buildup. You've got to do maintenance. You've got to keep that chemistry in the water that's in those tubes stays there. So you have to keep that chemistry controlled. We don't want algae or other growths in the tubes themselves. Already said the maintenance is in occupied spaces. It generates noise, not outside the building, but like each of those heat pumps is a compressor, and it's in the space that's occupied. And probably one of the major disadvantages to a school ground source heat pump system is that the noise that they can generate within the space themselves can be fairly objectionable. All right, you have to re-landscape after you're done drilling the wells. They're less efficient than a large water-cooled chiller. There's a unit in every room. Low heat transfer over time as buildup occurs. If the tubes start to corrode or build up sludge in them, as the heat exchangers get a little dirtier over time, you're going to lose a little bit of heat transfer. Okay. All right. Applications. They're really common in residential. They're very common in schools. Not as common as they used to be, but but pretty common. All right. Talking about the different loop systems. The wells in the ground, that's the vertical system that goes deep. The horizontal one is where we just dig a trench and put it in about 6 feet or so, 5 or 6 feet down. Even though the wells don't exchange water with the ground, they still need a permit. Anytime that you are digging a hole down, and I want to say deeper than 20 feet, I believe, the DNR requires you to have a well drilling permit, even if you're not pulling water up out of that well. All right, so just understand that. That's also what goes into making them so expensive, is you have to have a certified well driller doing it. All right. Here's some pictures of the Great River Medical Center. But those were already on the slides. Here are some diagrams of the different vertical systems. Let's see here. This is kind of a diagram of a horizontal system. And then a picture of some loops that are getting ready to be buried. There on page 21. All right. I'll just let you look through the various diagrams. All right, next is air handlers. Okay, so let's pause there on heat pumps. Remember, some tips for the class. Remember to keep in mind advantages and disadvantages as I'm comparing them to other systems. There is no perfect mechanical system. All right. And what changes from the best, what's the best system, changes with the size of the building, the physical location of the building, how much space is available, how important energy efficiency is to owners, and really changes with costs in energy. A note, we're going to talk about energy efficiency a little bit more later in the class, but understand when a client says, I want an efficient system, as engineers, we're thinking, all right, efficiency as in how good is it at burning gas and turning it into usable heat? Or how good is it at using electricity and transferring heat into a building? That's not quite what a building owner is meaning when they say efficiency. What they really mean is cost effectiveness. How efficient is it dollars per heat in the building or dollars per cooling effect for air conditioning? So what is the most efficient, and by efficient I mean the most cost effective, will vary based on your energy rates. And energy rates change over time. All right, we'll talk more about energy rates a little bit later in the class. So I'm going to get this published and get this for you to watch. And next time, we're going to start talking about air handler basics.